Hello friends, welcome back to our channel. Today we will see a concept of logical gates in digital logic design. So logic gates. So here the logic gates are classified into three categories. So one is a basic gates, universal gates, and exclusive gates. So why we require these gates concept? Okay, why the gate concept is required? So here, as we discussed, any digital system will be working based upon the binary numbers, that is either zeros or ones. That means the voltage level, so low voltage and high voltage. So where low voltage is represented with the zeros and high voltage represents with 1. So here in the digital systems, it will be using the digital circuits. So digital systems will be using digital circuits. Okay, and these digital circuits will be using these logic gates to make decisions, okay, mainly used in mobiles, computers, or any digital systems. In all digital systems, these gates will be used. Okay, so here the gate itself indicates the passing of information. So the input will be passed, right? So here the basic gates are AND, or, NOT. And coming to the universal gates, NAND, which is the opposite to AND, NOR, which is the opposite to OR. And universal gates, XOR and XNOR, right? So hope you understood. So all the digital systems will be designed with the help of a digital circuits, and in the digital circuits we will be using the logical gates to make the decisions. Okay, and also for computations we will be using this logical gates. And mainly the applications of logical gates, that means where it will be used means in mobiles or computers or any kind of digital systems, these logical gates will be used in these circuits. Now we'll see one by one each gate, the three things. So one is what is a Boolean expression representing that particular gate, and symbolic representation for every gate, and truth table. So if you give the inputs, what will be the output? Okay, truth table. So these three things we need to learn for all these gates, and or not, NAND, NOR, XOR, and no XNOR. Now let us start one by one. See, first, so here it is a gate name. What is a gate? So first we will take it as AND gate. Okay, and here we'll read Boolean expression. So what is a Boolean expression means? A dot B. So here AND is represented with a dot. Okay, next, symbolic representation. So symbolic representation, it will be taking two inputs, and for that two inputs the symbolic instruction will be in this way. This is the AND gate. Okay, and later I'll tell you the truth table. So truth table, let us take a truth table. Okay, let us consider the truth table here. Truth table. So if inputs A and B, so the combination of inputs, so we know that the language is a binary language, only zeros and ones. So the inputs will be 0, 0, 0, 1, 1, 0 and 1, 1. Now if it is a dot B, which is a end, so if both the inputs are true, then only the output is true. If any one of the input is false, the result will be false. So here 0 can be considered as a false and 1 can be considered as a true. So here it takes a two inputs. If any one of the input is false, automatically the result will be false. So here false, so the result will be false. 0 and 1 false, so here it is false. 1 and 0 false. So here both are true, so then only we'll be getting a true. So that's it. That is a boolean, AND gate. Next, OR gate. So OR is represented as A plus B, and the symbolic representation will be two inputs. It will also be taking two inputs, and this is the OR. This is the AND and this is the OR. And see here, A plus B. This is quite opposite to the logical AND. That means if any one of the input is true, the result will be true, otherwise it will be false. So if any one, so here two false, so obviously this is false. If here one is a true, so we'll get a true. Here also one is true, we'll get a true. Here one is true, we'll get a true. Right? This is the second gate. Next, we'll see not later. Okay, and now we'll see NAND. NAND gate. NAND gate means what is the end? A dot B and bar. A dot B bar. So that will be represented as two inputs and D, and here we need to give a small circle and give that. That is a NAND gate. So here it will be A dot B bar. So which is a quite opposite to the A and B, right? So if A and B is 0, you will get a 1. If A and B is 0, get 1, 1 and 0. That means if both are true, then only it will be false. If both are true, then only will be false. Okay. Next, NOR, which is A plus B bar. So this is also a similar representation, two inputs. So we'll take this one. So we'll take this one and give a small circle and here. So now A plus B bar. So which are quite opposite to the A plus B. So if both are false, then it will be true. So here it is a false, 0, 0 and 0. So the opposite to the A plus B. Next, XOR. XOR. So XOR is represented as A, this symbol and B. So this is the symbol for XOR, right? So XOR, which is represented with, again, one more line we have to take, two lines. So this is a symbol for XOR operation. Okay, so it is represented as A XOR B. So here, if both the inputs are either true or false, then only it will be false. If any one of the input is true and another one is false, it will be true. So here you can take A, B, 0, 0, both are equal, so it will be false. 0, 1, both are different, so it will be 1. Both are different, it will be 1. Again, both are equal, it will be 0. So if both the inputs are of the same, the result is 0, otherwise it will be false. Next, XNOR. XNOR means A plus B bar. So here also we'll be taking two things and small circle and write down. So this is the representation, symbolic representation of XNOR. So it will be considered as A XOR B bar, which is an opposite to XOR. So if both the inputs are same, the result is true. If both the inputs are false, different, then it will be false. So here it is 1, it is 0, it is 0, and it is 1, right? And not it takes only one value as an input, so it will be represented as a bar, so which is represented as symbolic representation. So this is the a bar. So it is only one input, it will take only one input. So I'll write the truth table here. A, either if it is 0 or 1, a bar will be, if it is 0 it will be 1, if it is 1 it will be 0. So quite opposite, okay, opposite to this particular thing. So this is the truth table of not operator, okay, not gate. So these are all different gates which we will use in the designing of logical circuits, okay. So from that circuit the inputs will be given and we'll be getting the output, okay. So here in the circuits, 0 is a low voltage and 1 is a high voltage, 0 voltage and high voltage. So these are the Boolean expressions. So I will write here Boolean expressions, and these are all the symbolic representations. Symbolic representation, and this is a gate. This is a gate. Okay, these are truth tables. All these are the truth tables. So hope you understood this one. And if you are having any doubts regarding this one, feel free to post your doubts in the comment section. Definitely I will try to clarify all your doubts. If you really enjoyed the session, like my session, share my session with your friends, and don't forget to subscribe to our channel. Thanks for watching. Thank you very much.